Hello dear students, this is Professor Anindya Das from Achievers. In today's video, we'll be solving the physical portion of phase 1 test 2 of Achievers level test series for IIT JAM 2025. Okay. So, at first, let's move into the MCQ portion of the question paper. And let's ponder into this particular question. All of you look into this particular question. This is a very familiar problem on chemical kinetics. You see, the elementary steps of a reaction are as follows. A plus B in equilibrium to 2C, and the equilibrium is a first equilibrium, it's a rapid equilibrium. It is followed by a slow step where 2C is converted into D. It's a slow step. So, the rate of product formation is proportional to which of the following? So, that means in this particular case, you are given a mechanism and you need to derive the rate equation from this particular mechanism. Okay. So, at first, we need to clarify the key facts related to this particular problem. If it is a multi-step process like this, then the rate of product formation, what is the rate of product formation? For a multi-step reaction, what is the rate of product formation? What is the rate of product formation? So, at first, this key fact has to be kept in mind. So, key fact 1. For a multi-step reaction, the rate of the reaction is actually the rate of formation of the final product. In this particular case, it is given the rate of product formation. Even it is not given in the question paper, the rate of product formation. If it is given the rate of the reaction, then also you have to keep a certain thing in mind, that if it is a rate of, the rate of the reaction, then also it is understood that it is the rate of formation of final product if the reaction is a multi-step reaction. So, for any multi-step reaction, the rate of the reaction is nothing but the rate of formation of the final desired product. Okay. So, this is key fact 1. This is key fact 1. And now, key fact 2. This is very important. If you are unaware about key fact 2, then you will not be able to solve this particular problem. So, in order to solve this problem, you must be aware of key fact 2. This is very important. And you will see there will be a lot of questions in chemical kinetics which can be solved if key fact 2 is known to you. So, this is very important. This is very important. So, key fact 2. Before moving into key fact 2, let us ponder into this particular mechanism once again. You see, this is the mechanism of the multi-stepped chemical process. In the first step, there is a rapid equilibrium. This is a rapid process, a fast process. Step 1 is a fast process. And step 2 is slow. Slow means this is the rate determining step, RDS. So this is known to all of us. Now key fact 2 is, see, if a rapid equilibrium is followed by the RDS, this is the condition satisfied over here. A rapid equilibrium is there, it's a rapid equilibrium that is followed by the RDS. So this condition is satisfied over here. A rapid equilibrium is being followed by the RDS. So if a rapid equilibrium is followed by the RDS, then the equilibrium of the former step will remain undisturbed. What does that mean? A rapid equilibrium step is followed by a slow rate determining step. So the slow rate determining step, this will not disturb the previous rapid equilibrium step. So the previous rapid equilibrium step will not be perturbed or disturbed by this slow rate determining step. That means the equilibrium of the previous step will remain maintained throughout the process. That is the consideration or approximation we must make in order to solve this particular problem. So this approximation has to be considered for solving this particular problem, that if a rapid equilibrium step is followed by the RDS, then the equilibrium of the previous step should be maintained all throughout the process. Okay. So this thing has to be kept in mind. So if you are aware of the second key fact, then obviously you will be able to solve this particular problem. Now the solution is damn easy. You see, according to key fact 1, for a multi-step reaction, the rate of the reaction is actually the rate of formation of product. So from key fact 1, one can say that the rate of the reaction V is nothing but rate of formation of product, that is dd dt. ddt of concentration of D. And if the rate constants of the steps are like, for the first step, step 1, for forward reaction the rate constant is K1, for the backward reaction the rate constant is K inverse 1, and for the second step let the rate constant be K2. So from the second step, obviously it's a single step. For a single step, order and stoichiometry are same. So for this particular single step, the order of the reaction or order of this particular process with respect to C will be 2, because for a single step, order and stoichiometry are same. So this will be equal to K2 multiplied by concentration of C square. Because concentration of C will be raised to the power 2. Why? Because the order is 2. For a single step, order and stoichiometry are same. So this is my equation number 1. And from key fact 2, one can infer that the equilibrium will be established. The equilibrium will remain unperturbed, undisturbed. That means the equilibrium of the first step will hold true. That means equilibrium constant K equilibrium, which is nothing but K1 by K inverse 1, should be equal to C square divided by concentration of A multiplied by concentration of B. So this is my equation number 2. As simple as that. As simple as that. The expression of the equilibrium constant can be easily written from the given mechanism. Okay, and we know that the equilibrium of the previous step with respect to RDS will be established, and that's what is written over here. Now you see, in equation 1, the rate is basically equal to K2 multiplied by concentration of C square. But concentration of C is basically the concentration of the intermediate, because C is the intermediate. So you have to express the concentration of C in terms of concentration of the actual reactants, that is A and B. And that can be done from equation 2. From equation 2, you see, from equation 2, you can easily write concentration of C to be equal to square root of K1 by K inverse 1 multiplied by concentration of A to the power half multiplied by B to the power half. This particular expression is quite evident from equation 2. So this is my equation number 3. Now you have to combine equation 1 and equation 3. You have to combine equation 1 and equation 3. So combining 1 and 3. What happens? V equal to K2 multiplied by C square. So what is square of C? You just squared this one. Square of the concentration of C. So what is the square of this? The root will be cancelled. So K2 multiplied by K1 divided by K inverse 1. Multiplied by concentration of A multiplied by concentration of B. Power half will be cancelled. So this becomes my final expression. So V is obviously proportional to concentration of A multiplied by concentration of B. So A is the correct answer. So A is the correct answer. So this is a very conceptual problem, but it is a typical problem. So the key facts of this problem has to be kept in mind in order to crack this particular problem. Okay. Okay. So you have to decipher the meaning at first, and then you got to relate that with the key facts, and then you can easily solve this problem. Okay. So this is my first question. Now let's move on to the second problem. It's an MSQ problem. Now students, let me tell you, there is a wrong notion that in MSQ problem always there will be a situation where more than one answer will be correct. Always there is more than one answer correct, but that is not true. An MSQ problem can always be an MCQ problem. MCQ is a subset of MSQ. In MSQ problem, either there can be more than one option correct, or it may also be a MSQ where a single option is correct. Okay. So in MSQ, you have either one option correct or more than one option correct. That has to be kept in mind. I am not saying that in this particular problem one option is correct. It's not that. It may be that also. I don't know. Let's solve this problem. In order to solve this problem, you have to read the problem line by line. And while reading the problem, you have to gather the data at first. Then only you will be able to solve the problem. So let's look into the problem. In the following gaseous phase first order reaction, so it's a first order reaction, see? It's a first order reaction. N is equal to 1. And also we are acquainted with the fact that A equal to A naught multiplied by e to the power minus kt. Similarly, you have ln A naught by A equal to kt. Okay. It's a gaseous phase reaction. So what happens in a gaseous phase reaction? Partial pressure of any component I is the general component, where I can be A, B, C. Okay, in this particular reaction, for this particular reaction, I can be A, B, C. So Pi is equal to concentration of I multiplied by RT. This is directly coming from the ideal gas equation. I think you all are acquainted with this particular equation. Pi multiplied by total volume equal to Ni RT. Now Ni divided by total volume is concentration of I. So Pi equal to concentration of I multiplied by RT. Now here T is constant. So if T is constant, then Pi is proportional to concentration of I. So if you compare these two cases, then you can say that as the proportionality constants will get cancelled out, so partial pressure of A equal to Pn naught multiplied by e to the power minus kt, and here you can say that ln Pn naught by Pa is basically equal to kt. So you can always write this because the proportionality constants will get cancelled out. RT will get cancelled out from both sides or from numerator and denominator. So you can always write these equations. You can always replace concentrations by partial pressure. So these are the key facts over here. These are the key facts over here. And another important fact for first order reaction is TF is equal to ln 2 by K, or ln 2 is 0.693 divided by K. And TF is independent of the initial concentration, and similarly it is independent of the initial pressure. So these are the facts that have to be kept in mind before solving this type of a problem. So now let us look into the data. The initial pressure was found to be initial pressure of A means Pa naught was found to be 400 millimeter of mercury. And they're saying that it changed to 1000 millimeter of mercury after 20 minutes. So this is at T equal to 0. And at T equal to 20 minutes, they're saying that the total pressure is 1000 millimeter of mercury. So this is P at 0 minute and this is P at 20 minute. So P at 0 minute is Pa naught. which was 400 millimeter of mercury, and after 20 minutes, P is 1000 millimeter of mercury. This is given. This is given. And these facts are known to us. Now let us look into the options one by one. The first option is half-life for A is 10 minutes. Is this option correct? In order to find out the half-life, what is needed to be known? The rate constant is needed to be known. So how can you calculate that? That is the first question. How can you calculate that? Is it possible to calculate that from here? From the given data? So at first let's look into this particular data, P20. What is P20 comprised of? After 20 minutes there will be A, there will be B, there will be C. So P20 basically comprises of PA plus PB plus PC. Okay. That has to be kept in mind. Now let's write down this mechanism once again. A to 2B plus C. So initially at t equal to 0, this was PA 0, this is 0, this is 0. After some time t, any general time t, this is PA 0, say minus P dash. So P dash amount of pressure decreases because A is consumed. So according to the stoichiometry, 2P dash will be formed with respect to B and P dash will be formed with respect to C. So what is the value of PT? P at time t. P at time t should be equal to P naught A minus P dash plus 2P dash plus P dash. So this minus P dash and plus P dash will cancel out. So it becomes P naught A plus 2P dash. So obviously, if you relate these two equations, then P at 20 is nothing but PA naught plus P 2P dash plus 2P dash. T equal to 20, P dash amount has decreased. Okay. Now P20 is given as 1000. What is the value of PA naught? PA naught is 400 plus 2P dash. So what is the value of P dash? The value of P dash is 1000 minus 400, that is 600 by 2 means 300. Okay. So now from here, you see, what is the value of PA? PA is PA naught minus P dash. PA naught is 400, P dash is 300. So 400 minus 300. Means 100 millimeter. Now you substitute the value into this particular equation. Therefore, ln PA naught 400 divided by PA. PA is 100 equal to K multiplied by 20 minutes. T is 20 minutes. So what is the value of K? K is 1 by 20. This is ln 4. ln 4 means 2 ln 2. This much minute inverse. The unit will be minute inverse. So ln 2 by 10. What is ln 2? 0.693. So ln 2 by 10 will be 0.0693. So the answer is 0.0693 minute inverse. So you got K. K is 0.0693 minute inverse. Now what is T half? T half is 0.693 by K. So 0.693 divided by 0.0693 minute inverse. That is 10. So this is 10 minutes. So you have got T and you have got K. So half-life is 10 minutes. That is correct. Rate constant is 0.0693 minute inverse. That is also correct. You will find everything now. Next option, option C. Partial pressure of C at 30 minutes is 350 millimeter. At 30 minutes is 350 millimeter. So you can't use the value of this P dash. You can't use, because this P dash is defined at 20 minutes. This P dash is defined as 20 minutes. So you have to calculate the value of P dash at 30 minutes. How can you do that? This is very easy. See, you use this particular equation. ln PA naught, sorry, by PA equal to KT. You use this particular equation. If you use this particular equation, what you are getting? See, ln PA naught is 400. PA is unknown. K is known. 0.0693 minute inverse multiplied by 30 minutes. So it becomes unitless. So from here you can solve the value of PA. And PA naught is equal to, PA is equal to PA naught minus P dash. So if you know the value of PA, you know the value of PA naught, so you can find out the value of P dash easily. And B is nothing but 2P dash, so double it, you'll get the result. So how will you get the result? Once again, you are aware of the fact that this P dash cannot be used because this P dash is found out at 20 minutes. So you have to find out the value of P dash at 30 minutes because we know that 2P dash is B. B is 2P dash. So this is very easy. At first you calculate PA by using this particular equation. So you substitute all the other values. PA is the only unknown. So you'll solve it. You'll get the value of PA. If PA is known, we know that PA is equal to PA naught minus P dash from this particular equation. PA is known. P naught is known. So easily you'll find P dash to be equal to PA naught minus PA. You'll find out the value of P dash. Now you double it, you'll get the result. And see, and if you solve it on your own, you'll see that you'll arrive at this particular result. The solution is given in the PDF. And the total pressure at 30 minutes is 1100 millimeter. That also can be easily found out because total pressure is PA naught plus 2P dash. You know the value of PA naught. Now you have solved the value of P dash. So you put the value of P dash over here. You'll get the result. PA naught plus 2P dash. And you'll see this option of total pressure being 1100 millimeter is also correct. Just put the values in the calculator and get the result. So this problem is basically a revision of the entire first order kinetics. And I think you all have understood this one. The approach is very simple. Now let's move on to the next problem. This is the final problem that I will be discussing over here. Before reading the problem, you have to understand one thing. What is the nature of temperature dependence of rate constant? What is the nature of temperature dependence of rate constant? You see, for any single step, say the step is I, dln ki dt equal to ei by RT square. Okay. And from here one can write Ki equal to Ai into e to the minus Ei by RT. So this is Arrhenius equation. The first one is the differential form of Arrhenius equation, and the second form is the integrated form of Arrhenius equation. This is defined for a single step. For a single step, for any single step, this Ei is positive. And as this Ei is positive, so dln Ki dt is positive. That means with increase in temperature, the rate constant will increase. With increase in temperature, the rate constant will increase. Okay. So this is all about a single step. Now what about a multi-step process? What about a multi-step process? Well, is this equation also applicable for a multi-step process? Is this equation also applicable for a multi-step process? Yes or no? Is the Arrhenius equation applicable for a multi-step process? The answer is a bit confusing. The answer is a bit confusing. See, you can write dln K dt equal to Ea by RT square, where K is the overall rate constant and Ea is the overall activation energy. You can write it. But there is a confusion. In this particular case, you will see Ea can be positive, can be 0, can be negative. It is not certain that as compared to the previous case, Ea should always be positive. For a single step, Ei, rate constant, activation energy for a particular single step is always positive. That is always true. But when you are talking of a multi-step process, the activation energy can have all the three possibilities. It can either be positive, 0, or negative. It's a real number, obviously, but it can either be positive, negative, or 0. Anything can be. If it is positive, then what happens? dln K dt is positive. That means with increase in temperature, the overall rate constant will increase. But if it is 0, then with increase in temperature, K will remain constant. That means K becomes independent of T. Overall rate constant becomes independent of temperature because dln K dt is reduced to 0 over here. And in case Ea is negative, RT square is always positive. So if in case Ea is negative, then what happens? dln K dt is ought to be negative. If dln K dt is negative, then with increase in temperature, the overall rate constant will decrease. So it may so happen that with increase in temperature, the overall rate constant is decreasing. And it is not a violation of Arrhenius equation because Arrhenius equation is valid only for a single step, both the equation and the condition that with increase in temperature, the rate constant will increase. So with increase in temperature, the rate constant will increase. This concept is valid only for a single step or an elementary reaction, which is comprised of a single step. But if it is a multi-step process, then the form of the differential equation is valid, but the condition that with increase in temperature, the overall rate constant will always increase is not valid. There can be three options. Either with increase in temperature, the overall rate constant is increasing or decreasing, or it is indifferent to the variation of temperature. So all the three cases may be possible. Now, if you are given a rate constant, overall rate constant, how can you find out the value of the activation, overall activation energy? So this is the problem. So you have to be aware of two important key facts. Key fact 1. Actually, key fact 1 will be applied for solving this type of a problem. And I will also show you key fact 2, which will be applied for solving different types of problems. So I will come to that later. At first, let us ponder into key fact 1. So what is our objective? Our objective is very simple. Overall rate constant is given. You have to find out overall activation energy. So this is our objective. This is our objective. Overall rate constant is given. You have to find out the overall activation energy. Now, for key fact 1, basically the overall rate constant is a multiplicative combination of the individual rate constants. Overall rate constant is a multiplicative combination of the individual rate constants. That means if the individual rate constants are multiplied together or divided, then the overall rate constant is constructed. And in key fact 2, we'll use the additive combination. So there are two options. In both the options, we need to find out the overall activation energy from a given expression of rate constant, overall rate constant. Now, overall rate constant is basically a combination of the rate constants of the individual steps. And the rate constants of the individual steps can either be combined in a multiplicative manner, which I will be discussing in key fact 1, and they can also be combined in additive manner, that I will be discussing in key fact 2. So in key fact 1, K is the multiplicative combination of the individual rate constants. Actually, in this particular problem also, it's a multiplicative combination of the individual rate constants. See, K1, K3, K4 by K5 all to the power half. So it's a multiplicative combination. So in general, let us do the general approach at first. In general, K is equal to pi I, Ki to the power, say Ai. Pi I is the symbol for a multiplication series, and Ai is the power to which Ki is raised. If AI is negative, the term is situated in the denominator, and if AI is positive, then the term is situated in the numerator. That is known to all of us. So this is basically K1 to the power A1, K2 to the power A2, K3 to the power A3, and so on. So what is the general procedure? At first you take log of both sides. ln k equal to A1 ln K1 plus A2 ln K2 plus A3 ln K3 and so on. You can write it in this way. So basically it becomes a summation series. AI ln Ki. It basically becomes a summation series. So if you take logarithm of a multiplicative series, it becomes a summation series. Now you differentiate both sides with respect to temperature. A1 dln K1 dt plus A2 dln K2 dt plus A3 dln K3 dt and so on. Now the final step, you see. What is dln k dt? dln k dt is EA by RT square. So write EA by RT square for dln k dt. What is dln K1 dt? dln Ki dt is EI by RT square. Here I is 1. So it becomes E1 by RT square. And there is a coefficient A1. So A1 E1 by RT square plus A2 E2 by RT square plus A3 E3 by RT square and so on. Now the RT square terms will get cancelled out. So EA becomes A1 E1 plus A2 E2 plus A3 E3 and so on, which is nothing but summation over AI EI. But in exam hall, especially when it is a competitive exam, you can't go on solving this lengthy procedure. You can't go on solving this lengthy procedure. In that course, you will be losing time. You will be losing time. You will be losing time. Just remember one thing. In case of overall rate constant expression, the powers of the individual rate constants will become coefficients for overall activation energy. See, I am repeating it once more. When you are considering the expression of overall rate constant, then you will see that the individual rate constants are raised to certain powers, AI, A1, A2, A3, etc. Now, if you convert it into overall activation energy, then you will see that in that expression, the multiplicative combination has become an additive combination at first. The multiplicative combination has become an additive combination at first. And in case of overall rate constant, you found that the individual rate constants were raised to certain powers. Now, in case of overall activation energy, you will see that the powers has become the coefficients. The powers has become the coefficients of what? Of the individual activation energies. So the fact is very simple. Just keep this thing in mind. I am raising this. Just keep this thing in mind. Key fact 1. This is multiplicative. It becomes summation over AIEI. This is additive. So for a multiplicative rate constant combination, you'll find an additive activation energy combination. If the overall rate constant is multiplicative, the overall activation energy is additive, number 1. And the powers, this was power, and now it has become coefficient. The same thing which was power has now become coefficient. So if you keep this thing in mind, you can solve the problem very easily. Now, in this particular problem, you see, the overall rate constant is given K equal to K1, K3, K4 by K5 whole to the power half. Just expand it in the way it was done here. K1 to the power A1, K2 to the power A2, K3 to the power A3. So it becomes K1 to the power half, K3 to the power half, K4 to the power half, and K5 to the power minus half. It's quite clear. So what will be the expression of activation energy? It's very simple. Activation energies will be an additive combination. How many terms will be there? If there are 4 terms in the expression of the overall rate constants, then there will also be 4 terms in the expression of overall activation energy. 4 terms. So E1, E3, E4, E5. What will be the coefficients? Here the powers will become the coefficients. So the power is half, the coefficient is half. The power is half, coefficient is half. The power is half, coefficient is half. The power is minus half. So this sign becomes minus, the coefficient is minus half. As simple as that. Now they have given the overall activation energy to be equal to 265 kilojoule per mole. EA1 is given 350, so it becomes 350 by 2. EA3 is given 160, so it becomes 160 by 2. EA4 is given, it's 10Y by 2. EA5 is given 10, so minus 10 by 2. So it cancel this, it becomes 175. If you cancel this, it becomes 80. If you cancel this, it becomes 5. If you cancel this, it becomes 5. So you have got 265 minus 175. minus 80 plus 5. So 265 plus 5 is 270. 270 minus 175. This is 95. 95 minus 80, it's 15. So basically you get 15 equal to 5y. That makes y equal to 3. So what is the value of y? The value of y is 3. So this is all about the multiplicative combination. What if it was an additive combination? So let's move on to key fact 2. We have solved problem 4. But let's move on to key fact 2. Key fact 2 is very important. What happens if it is an additive combination? So let's move on to key fact 2. If K is an additive combination, A1 K1 plus A2 K2 plus A3 K3 and so on, what will happen? We know that for ith step, dln Ki dt equal to Ei by RT square. That is known. But the problem is that you can't take log now. If it is multiplicative, then if you take log, say if it's AB, then if you take log, it becomes ln A plus ln B. Now if it is A plus B, then what is the use of taking log? ln of A plus B cannot be split into two terms by applying the property of logarithm. So you have to apply a trick over here. What is the trick? You see, dln Ki is nothing but dki by Ki. So dln Ki is replaced by dki by Ki. Dt remains as it is, equal to Ei by RT square. Therefore, dki by dt equal to Ei Ki by RT square. Bas. Now you have cracked the problem. Now it's very easy. You just need to differentiate this equation. So dk dt is, A1 is constant, it goes out of differentiation, dk1 dt. A2 is constant, goes out of differentiation, dk2 dt. A3 is constant, goes out of differentiation, dk3 dt, and so on. Now what is dk dt? What is dk dt? Again, for overall also we know that dln k dt equal to Ea by RT square. So similarly you can say that d overall k dt equal to Ea multiplied by K by RT square. By same logic, by same mathematical logic, d overall k dt equal to Ea into K by RT square. So write it in this way, overall activation energy multiplied by overall K by RT square equal to A1 E1 K1 by RT square. dk1 dt is E1 K1 by RT square. dk2 dt is E2 K2 by RT square. This is E3 K3 by RT square. And the series continues in this manner. RT square will get cancelled out. So Ea becomes A1 E1 K1 plus A2 E2 K2 and so on divided by K. Now you know k is summation over ai ki. So finally EA becomes C, in the numerator it becomes summation over ai ki. And what in the numerator? In the denominator it has become summation over ai ki. And what about the numerator? In the numerator it has become summation over ai ei ki. This term. So if it is an additive combination, then you can solve it in this particular manner. So thank you all students, and bye bye for now.